Have a go at these three questions before we begin. First one, we're throwing a ball upwards with a speed of 15 meters per second from a height of 20 meters. We want to know how fast it's going when it lands at the bottom. In the second question, you throw the ball downwards from the same height of 20 meters, and you still want to know how fast it's going when it lands. For the third one, this might be a little trickier. You'll have to think separately in terms of horizontal motion and vertical motion. Throw the ball horizontally, so perfectly sideways, with a speed of 15 meters per second. Still from a height of 20, eventually the ball will land. How fast will it be moving when it lands? Pause, have a go at these questions, and then come back and we can compare answers. Just remember to use g equals 10 to get nice, easy, round numbers for your answer. This first question is a SUVAT problem. We have a constant acceleration downwards of g, or 10 meters per second per second. The initial speed is in the upwards direction, so u equals positive 15 if we're treating up as positive. And we also have a negative displacement, so negative 20 for the value of s. The most efficient formula for finding the final speed is v squared equals u squared plus 2as. So if you sub in your numbers, you'll end up with v squared equals 625. The only reason I know that this corresponds to v equals minus 25 is from the context of the question. This formula will not tell you which direction the thing is moving at the end. It'll only tell you the square of the velocity, which means I have to use context in this case to work out whether it's going to be a positive or a negative velocity. In this particular case, because the thing will be moving downwards at the moment when it hits the ground, the vertical velocity must be negative 25. But of course, if I'm just interested in the speed, that's the size of the velocity, so we end up back at 25 meters per second. If you've done question 2, it's very similar, but we have to change some of the signs around. If it's thrown downwards and it's accelerating downwards and it's moving downwards, then actually u and a and s are all going to be in the downwards direction. And if, like me, you like to treat up as positive, that means you'll end up with an equation with lots of negatives in it. But it's okay, because as long as you're consistent, it'll still work out just fine. In fact, we get the same result as last time, and I still know that it's going to be moving downwards when it lands, so I know that the vertical velocity is negative, but of course the speed is just the size of the velocity. The third one is the most interesting, and if you've looked at some year 2 applied chapter 6, then you'll know a bit more about how motion works when you're treating it as two different directions. We can look separately at horizontal motion and vertical motion. If it's thrown horizontally, it's not moving up and it's not moving down, so the initial speed vertically is 0. And it turns out you can sub that in the equation and you can calculate that at the moment when it lands, it has 20 meters per second of downwards velocity. But that's not the end of the story, because it also has 15 meters per second of horizontal velocity. If you think about it, the only force acting on the object while it's in motion is its own gravitational force pulling it down. We're assuming, for the sake of argument for all three of these questions, that there's no effect from air resistance, for instance. But once we've got the horizontal component of the speed and the vertical component, we can put them together. We can combine them with Pythagoras to get the overall speed, because the direction it's moving will be partly sideways but partly vertical. And it turns out, once again, we end up with 25 meters per second. It's worth considering what happens when you change the direction of projection to all sorts of other things. We've looked at perfectly vertically upwards, vertically downwards, and even perfectly horizontal, where we're aiming it completely sideways. But it turns out you can mess with that angle however you like, and the final direction will change, but the final speed will not. So that's interesting. We can go a step further and think about motion on, say, a roller coaster. So what seems to be happening here is independent of the path taken by the particle. If the particle has a speed of 15 meters per second at the beginning of motion, and then it loses 20 meters of height, then somehow it has 25 meters per second of velocity or speed at the end of motion. A few things to notice here. The initial direction doesn't matter. The shape of the path doesn't matter. If you start with 50 meters per second of speed, by the time you've traded in your 20 meters of height advantage, you will have increased your speed to 25 meters per second. what's going on? Well, as you might have guessed by the title for this, we're talking about energy here. A more fundamental reason behind this, which you can get at without needing to worry about whether acceleration is constant, which it certainly isn't for the roller coaster scenario, is to consider exactly where all that movement energy is coming from. And in this case, basically, the movement energy that we collect along the way comes from gravitational potential energy. If you're at a height, you have the potential to convert that height into motion. All particles require energy to move, and all moving particles have energy by virtue of being in motion. Their energy can come from various places. For instance, a car that's moving has probably gained that kinetic energy by converting chemical energy from its fuel or electrical energy from its battery. And if you have kinetic energy, then you can convert it to other things. You could cycle into the back of a wheelie bin and then convert some of your kinetic energy to kinetic energy in the wheelie bin, or indeed to heat and sound from crashing into a wheelie bin and causing it to spill all its contents. Typically, a lot of energy is wasted or lost when you have a collision like that. Not lost in the sense that it's destroyed or disappears, but in the sense that it dissipates and can't easily be recollected and reused. We have an official definition for energy, and people who study physics will have come across this before. The work done by a force is another way of saying the energy transferred by a force, and it's simply equal to the total size of the force multiplied by the overall distance that the force is acting on the object for. This explains why you don't actually use energy just by resting a heavy thing on top of something else. There's definitely a force there, but your brick that you've left on top of a pile of papers in the garden is not transferring energy because it's just sitting still on top of the pile of papers. If, however, you take a force and apply it over a distance, then energy is transferred. This is how things are accelerated, for instance. If you apply a force for a certain length of time, then the object will move a certain distance, and as a result, it will end up going faster. So we can think about what happens with a 12 kilogram box pushed 5 meters along a smooth surface with a force of 30 newtons. Essentially, the energy that we're producing here by applying this force over a given distance is going to be kinetic energy, which just means movement energy. You can use F equals ma to work out how fast the box will be going if you start from rest, because you know how far it goes and you know the size of the force acting on it. You also know the mass of the object. But we can work out the work done by the force first of all. We get 150 Newton meters, which is the same as 150 joules. That's what a joule of energy refers to. 1 joule is the amount of energy transferred by a 1 Newton force acting for 1 meter of distance. Now, if we remove that force and the box slides onto a rough section of the surface, let's say we've got a frictional force of 60 newtons, how far will it travel during the deceleration phase? In this case, what's happening is there is kinetic energy that the particle already has because it's gained it by having a force acting on it for the first 5 meters of its journey. In fact, it's gained 150 joules of movement energy or kinetic energy. And all that energy is going to eventually be lost to the surrounding environment in the form of heat, sound, vibration, and that's thought of as the work done by friction, or the work done against friction, if you like. Essentially, friction is acting in the opposite direction to motion, so we're having to trade in the kinetic energy in order to move forwards against the resistive frictional force. And you can work backwards. You can say we've got a force of 60 newtons acting for a distance of x meters, and the total amount of energy that's going to be transferred by that force, or transferred to that force from the object, if you like, is 150 joules. And you can work backwards and find that you're going to travel 2.5 meters. The great thing about this is a lot of these calculations you could do with SUVAT in this particular case, but you can often do more efficiently with energy considerations. And crucially, when SUVAT equations fail because the force is not constant, we can still use this concept of energy being the product of force and distance to calculate things when you couldn't use constant acceleration equations. Let's have a closer look at how work done is connected to the speed of an object. So in this particular case, I'd like you to pause the video and have a think about how you can deal with a general object of mass m accelerating from rest from a speed of 0 up to a speed of v meters per second as a result of a force F being applied over a distance s. Remember, you can use Suvat equations because it's a constant force and therefore there'll be a constant acceleration. So you've got F equals ma that can connect the force and the mass and the acceleration, and then use Suvat equations to find something connecting mass, velocity, force, and displacement. Give it a try and then unpause the video. The next bit of the question is going to come up in just a moment. Okay, the next part, once you've tried the first bit, is notice that when you have force multiplied by distance, that is the definition of energy or work done. So now go back to your equation, find F times S, replace it with E, and then rearrange and make E the subject of your equation. See what you discover. All right, for the first bit, let's see what happens when we put in F equals ma and the equation we used earlier, V squared equals U squared plus 2AS. Because we want the acceleration for the Suvat equation, we're going to replace A with F over m. And when we sub in 0, because we accelerated from rest, we end up with V squared equals 2Fs over m. And remember, E, the energy, is F times S. So the next step is going to be replace Fs with E, rearrange to make E the subject, and out pops a formula that will look very familiar to anybody who's done even GCSE physics, presumably. E equals half mv squared. The energy that a force provides to an object while accelerating it up to a speed of v is half mv squared. If it starts from rest, the total amount of kinetic energy it will produce is half mv squared. So essentially, if it starts from rest, it has no kinetic energy whatsoever at the beginning. Then you apply a force and kinetic energy is produced. There is a second important type of energy that we're going to get into at this point, and that's gravitational potential energy. It's called potential energy because it doesn't manifest itself quite as obviously as kinetic energy. It's energy you have just by virtue of being not at the center of the Earth. You can think of that energy as being more obvious when you're standing precariously on a shed and the Earth is a couple of meters below you, and you know that if you move too far in one direction, then suddenly your gravitational potential energy will be converted rapidly into kinetic energy and you'll land heavily on the ground and maybe sprain an ankle. Now, gravitational potential energy is easier to derive than kinetic energy. It's literally the force that's acting on you, gravity, m times g, your weight, multiplied by the distance you cover, which is h, the change in your height. So we can, just like a bank account, you can think of these two as being different accounts that you can transfer money between. Only in this case, it's energy. And as long as no energy is added to a system and no energy is removed from a system, you know that whatever you had at the beginning is the same as what you're going to have at the end. So we can use that to solve problems like the roller coaster problem. You can use this formula to work out the total amount of initial kinetic energy. And then you can use the gravitational potential energy formula to work out the initial gravitational potential energy. Then you can add those two together to work out the final kinetic energy. Notice that by the end, we've used up all the gravitational. So once you've got no more gravitational potential energy, all your energy must be in the form of kinetic. Now, yes, technically, you're still above the center of the Earth at this point, but it makes sense to use an arbitrary point as the baseline or the ground level. Just like you wouldn't say, I just jumped off a 23-meter height if all you're doing is jumping off a wall that happens to be halfway up a hill. Your baseline is going to be just some logical place that you're going to assume is zero baseline. Have a go at working out these values, then come back and see what you can derive from those. Okay, so the first one here is kinetic energy at the beginning, half mv squared. The mass is 200 and the initial speed is 15, so I get 22,500. Initial gravitational potential energy, if you use G equals about 10, then you should be getting an answer of about 40,000 joules for this one, mgh. And then we just add those two together to get the final kinetic energy. And the beauty of this is, if you know that all of the energy is now kinetic, you can go back to your formula, substitute those values in, and work out the speed that corresponds to that.